Projectile problems involving vectors. In a previous video, we've already looked at finding various things like the height, the time of projection, and the range of problems involving projectiles. Now, in this video, we're going to look at projectile problems involving vectors. Now, if we look back to what we did in Mechanics 1, there's a couple of key points that we might need to use when we're tackling questions to do with vectors. Now, we're not going to use the top rule in this problem we're going to look at in a minute, but we are going to use the second rule. Now, the position vector is given as r equals r0 plus v times t, where r0 is the initial position of the particle, and after a certain time going at a certain velocity, it'll be at a new position vector. And some questions you're going to tackle in Mechanics 2 to do with projectiles and vectors will involve using that formula. Secondly, we need to remember that the magnitude of a velocity gives you your speed, and to find the magnitude of a velocity you do Pythagoras' theorem on both the I and j components of the vector. So you square the I and j components, add them together and square root them. If you can't remember how to do either of those facts, you need to go back into the Mechanics 1 section of the iTunes U video and watch the video on position vector and finding the magnitude of a vector. Now, let's have a look at an example of a projectile problem involving vectors. Here's an example. A cricket ball is struck by a bat at a height of 0.6 metres above the ground. Immediately after being struck, the cricket ball travels at a velocity of 6i plus 10j metres per second to the minus 1, where I and j are unit vectors horizontally and vertically respectively. After being hit, the ball travels freely under gravity until it hits the ground. Find the greatest height reached by the cricket ball, the speed of the ball when it hits the ground, the angle velocity of the ball makes with the ground on impact. Now, the first thing to do is to highlight the key points in this question so that we can draw ourselves a diagram to help us answer this question. So, there's a lot of information in this question that isn't of much use to us. For example, we don't need to know it's a cricket ball because we're going to imagine that cricket ball to be a particle. What is important is it is hit at a height of 0.6 metres above the ground, and that its initial velocity is 6i plus 10j. And other than that, we also know that it travels freely under gravity. So, now we've got a few bits of support information, we need to construct ourselves a diagram. So we've got our particle, and we know it starts off from a height of 0.8 metres above the ground. And once it's been hit by the cricket bat, it travels upwards, and it's going to come downwards, hitting the ground over here. So here's our ground. Right, we also know that initially this particle, or the cricket ball, has got a velocity of 6i plus 10j. Now, when we've looked at other projectile problems, we've had the angle of projection and the initial speed, and what we've then done is we've found the component of the speed that is acting upwards and the component of the speed that is acting horizontally. Well, as we are now given a vector velocity, we can actually decipher from here which part is the vertical component of the velocity and which part is the horizontal component. And it is from here. The 10j represents the vertical component and the 6i represents the horizontal component. So, in this direction, we've got our 6i, and in our vertical direction we've got our 10j. Now, that's all the information we know into our diagram, and the first thing we're asked to do is to find the greatest height reached by the cricket ball. So that means the greatest height here to the floor there, and to do that we're going to use suvat in the vertical direction. So suvat. And if we write down the parts we know, we can find out what the distance is from when the cricket ball was hit to the top, and then what we need to do is add on the initial 0.8 metres it is above the ground. So, Subat, we are trying to find the S. We know the initial component is 10. Now we're not going to put a J in here, we're just going to put 10, even though because we're just looking in the vertical component, so we know we're looking at a J component. We know that the final speed is 0. We know that it's going against the acceleration, minus 9.8, and there's no time. So we're looking for a Subat equation that doesn't include time, and that is v squared equals u squared plus 2as. So if we substitute in our values, so 0 squared equals 10 squared minus 2 times 9.8 times s. The minus is from the minus 9.8. And if we sort this out here, we end up with 19.6 s equals 100. So we've done 10 squared, and then we've done 2 times 9.8 times s and brought it over to the other side of the equation. So the s is equal to 5.1 metres. But this just represents the distance from when the ball was hit to the highest point. Remember, we've also got to add on this initial 0.8 metres from the ground. So the greatest height is going to be 0.8, add on our 5.1 to make up 5.9 metres. Now remember, we've only gone to two significant figures because our acceleration is given to two significant figures. Right, question B says find the ball at the speed of the ball when it hits the ground. Now, we know the horizontal component. If we look at the final section here and we look at what the horizontal component of the speed of horizontal component is, we know that is 6i. What we also want to know is we want to know the vertical component, and then we can find the actual speed of the particle as it hits the ground, or the cricket ball as it hits the ground. So we need to find this vertical component here, and to do that we can look at Subat again. And if we look at the displacement from where we initially started, it's going to be minus 0.8. We know what the initial speed is in the vertical part, it's 10. We know it's going against gravity, so minus 9.8, and then we can find out the final speed. So, part B, we're going to use Subat again. So we're not using time again. We know that's minus 9.8. We know that part is 0.8. We know the initial is 10. And the final velocity is what we are trying to find out. So the Subat equation we're going to use again is v squared equals u squared plus 2as. So we're finding our v squared, so substitute in the rest. So it's going to be 2 times minus 9.8 times minus 0.8. So minus 9.8 times minus 0.8 will give us a positive number, because a minus times a minus gives us a positive. So v squared is going to be equal to 115.68. So v, if we wanted to, v is equal to the square root of 115.68. Now, what that value has told us though, is it has told us that this section here, the vertical component, is the square root of 115.68. But what we want to know is what is this component of the speed in the direction that it's travelling as it hits the ground. So now we've got these two parts, we can use Pythagoras' theorem, because it's a right angled triangle, to find the speed of the particle as it hits the ground. So if we look at that triangle, we're going to do 6 squared plus this section here squared, which is just going to be 115.68, and remember we square root that, and if we do that we get the answer 12.31, but we've got to go to no more than two significant figures, so it's 12 meters per second to the minus 1 to two significant figures, and that is the speed at which our projectile, our particle, after being projected, or our cricket ball, will hit the floor at. That's the speed. The final thing we're asked to do is to find the angle of the velocity of the ball makes with the ground on impact. So it's back to our triangle again here. Now we know our J and our I component, we need to find this part here, our angle at which it hits the ground. So we've got our opposite and our adjacent, so we're going to use tan. So final section, tan of theta is going to be equal to the opposite, which is the square root of 115.68 over 6, which if you do that on a calculator you find out that theta is equal to 61 degrees. Now the reason we've kept it in the square root of 115.68 is to get the most accurate answer at the end. So when you're looking at problems to do with vectors, it's really important to draw the diagram and to remember that when you've got your velocity 6i plus 10j, you can split that into the vertical and the horizontal components separately. And then it's basically the same skills we've looked at on the other video, but at the end we might have to look at finding the speed of the ball as it hits the ground by using a right angle triangle. And on some questions you may have to use a couple of skills we've studied in Mechanics 1 to do a position vector and the magnitude of the speed.